We're doing this COVID style since I'm in Iowa with the soccer team. It's kind of a big deal. So from now on, like I mentioned, every day we'll start with an AP test question. Since I'm not there, I'm sure you're going to be super engaged in this question. So if you guys want to pause the video and give this a read, go ahead. This tends to be a more difficult question on the AP test, but go ahead and pause the video, try to answer it, and then I'll explain it. So 3, 2, 1, pause. All right, we're back. This is the definition of the derivative. There it is, x plus h minus f of x all over h. And the limit as h goes to 0. So this is the derivative, and they're telling you the derivative equals 5. That's what this says. Where is the derivative? It's right here at x equals 2. So the derivative at 2 equals 5. Well, if we have a derivative at 2, then we must be continuous at 2. If we have a derivative at 2 that equals 5, well then we must be able to take a derivative at 2. So this has to be true. And now there's only one answer possible because 1 and 2 have to be true. So certainly there's our answer, 1 and 2 only. Does the derivative have to be continuous at x equals 2? Well, the derivative of f, if this is f, and this is already the derivative of something, they're really saying, well, the derivative of this also has to be continuous. And that's not necessarily true. We don't actually have any information about the derivative of this, which we don't know. So that's the best we can do, is say 1 and 2 only. Off we go. So what are we doing today on Thursday? I'm sorry I missed you guys. I'm on the way to Iowa right now. But in the meantime, the key is that you guys understand this. This is Unit 3. We are talking about a derivative. All right, there's lots of ways to represent this, but basically it's just this. It is just a collection of slopes. How do we get that? Well, there's lots of techniques, analytical, there's ways to sketch, there's ways to graph, there's ways to explain in words, there's all sorts of ways to come up with a derivative, but it's just a collection of slopes. If you have a derivative that is a function, that is a collection of all the slopes of the function that came before it. You took a derivative of something, we collected all the slopes together, and boom, there's the function we came up with. Before we start learning all the procedural techniques, you guys need to understand the concept behind a derivative. So we do it visually first. We learn to collect slopes visually. So you guys have a set of graphs there, and you guys can do this at your own pace. But what we're going to be doing is we're going to be sketching. We're going to be sketching what the derivative looks like. Excuse me. The more you can talk yourself through this, the easier that this gets. But what are we doing? We're collecting slopes at every single point on a function. So we'll start very, very simple and then progress to something more difficult. If we're dealing with all linear segments, we can be very precise in this case. So the derivative is a collection of slopes. We are plotting the slopes of the function. So what we can do is pick any point on this function and then check and see what the slope is there. So let's say I'm down here, I'll just pick -4. When x is -4, right here, remember I'm not looking for the output right now. I don't care that this is the point -4, -1, that's not important. What I'm trying to sketch is the derivative. What would the derivative of this look like? Well, the derivative is the slope of the red line at -4. I need to ask myself, how steep is this? Or how fast is this changing? So at -4, what is the slope of this line right at this dot? Well, since it's a line, it's pretty easy to see the slope. I can kind of see this is going up 3 over 1, up 3 over 1, up 3 over 1. So the slope at x equals -4 of this red line is 3. So at -4, I would plot -4 comma 3, because that is the value of the slope. And we can play this game again. Well, since this is linear, the slope is going to be the same anywhere from here to here. The slope is always up 3 over 1, up 3 over 1, up 3 over 1. So if I pick this point right here on the graph at -3, the slope is 3. So I would plot that. What if I pick a different point? It doesn't matter where I pick, the slope is 3. If I picked over here -5, right here, the slope is 3. At -4, the slope is 3. At -3, the slope is 3. You get the idea. The slope is always 3. So we can sketch the derivative just by connecting the dots of the slopes. Now it looks like it stops here, so I'm going to have my derivative stop there. And we know from the other day, this is a corner, and you can't take a derivative at a corner. So if I'm sketching the derivative, the slope is 3, the slope is 3, the slope is 3, and then right here, the derivative does not exist. You can't take a slope at a corner. Well, then what happens? Now the behavior changes. Here's the original f of x. What is the slope of this portion of the graph at this point, or this point, or this point, or this point? Well, if I pick this point right here, at -1, 5, the slope at x equals -1 is 0. It's a horizontal segment. So when I'm sketching the derivative, I sketch the value of the slope at that point. Here I'm at x equals -1. The value of the slope is 0. So I plot 0. Maybe now you're picking up on this and you can go a little bit faster. So the slope here is 0, so I can plot 0. In fact, the slope of this entire segment is 0. We are undefined at a corner. We're undefined at a corner. The derivative does not exist there, but everywhere in between, the derivative exists. And now let's pick it up a little bit faster. Those of you guys that had physics, this will be very obvious to you. The slope of this line, we're going down 1 over 2, down 1 over 2. So the slope of this from 1 to 5 is constantly -1/2. We do not have a slope at a corner, so at -1/2 this picks up. It's -1/2, -1/2, -1/2, -1/2, and then we reach the end point where it seems we do have a slope at that very end point. This would be the sketch of the derivative, collection of slopes of each segment. Let's get a little bit tougher, shall we? So here is a random curve. Hopefully you recognize this to be some sort of x to the third type graph. And we'd like to sketch the derivative of this. Well, now we can't quite be as precise as we just were. These are not linear segments. This is varying. The slopes are varying at every single point. So this is the art of derivative sketching, is you guys have to learn to estimate. You want to estimate as accurately as you possibly can. So once again, we're given a function, and we want to sketch the derivative. We want to collect all the slopes and plot them on the graph. So I usually recommend starting with the most obvious places. Every point on this curve has a slope. You can pick them at random. But what is the slope at a point? Well, that was the whole point of the last couple days of class. It's the slope of a tangent line. If I draw a tangent line to a graph, that tells me the slope at a single point. F of x plus h minus f of x all over h. We're zooming in on a single point and coming up with the slope at one single point. So if I pick a random point on this curve, how steep is the curve at -4, whatever this is? What I'm really asking is, what is the slope of this line right here that just glances off the curve tangent to that single point? That would represent the value of the slope at -4. Well, here's where the wing it part comes in. About how steep is that line? You have to kind of estimate this. It's obviously going up and to the right, so it has a positive slope. And here to here, if I connected the corners of any of these grids, that would be a slope of 1. And it looks like that's pretty close to 1. It might be just a little bit steeper than +1. But this definitely has a positive slope close to or slightly above 1. So since we're just estimating, I'm going to put that on the graph. I'm going to take that tangent line off the graph, and at -4, the slope at that point is really close to +1. You can play this game 1,000 times until you have a collection of points, but you want to make sure your estimates are accurate. Your tangent lines have to intersect the graph just that one time. So let's pick a more obvious spot. How about at -2? At -2, looks like we hit a maximum here. As I'm graphing these tangent lines, it looks like this tangent line would glance right off the graph like so. Well, that's a really easy one. That makes sense to me. The curve, moving up the curve, I'm increasing, 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 and then I reach this highest point, I stop increasing, there's a change in behavior, and now as I start to sketch this, I'm decreasing, I'm going down. Well, the derivative's telling me that. It's saying, hey, your slope is steep, steep, not quite as steep, not as steep, not as steep, flattening out, flattening out, flattening out. Hey, we stopped increasing. Something strange is happening here. And then you started decreasing. So the slope at this instantaneous moment is 0. At a maximum or a minimum, we actually hit 0. Well, then that should make this point really easy. We're going to go down, hit this point, and go back up. So this point is also going to have that zeroed out tangent line. And the slope of the red curve at x equals 2, I can see right there is a flat line. So the slope is 0. We are plotting a collection of slopes. Let's keep going. I'd certainly like to know what's happening between -2 and 2. So at 0, there's a point right there on the curve. I'd like to know what the slope of that tangent line is right there. I'm just going to estimate. Clearly this is decreasing. It's a negative slope. And it looks like it's going down maybe 2/1, maybe 3/1, somewhere in there. It's definitely down, and it's definitely more than -1. So at 0, this point, the slope of this line at 0 is about, I'm just going to call it -2. Maybe you think it's lower than that, fine. And let's just get one more point on here and we'll have an idea of what the shape of this looks like. I'm going to plot a point over here at 4. So following the red curve, let's plot a point right here. And let's draw that tangent line. Basically follows the curve if we stay close. How steep is that, would you say? Well, the steepness of this green line, the slope of this green line is steeper than up 1/1. I can tell that. I'm going to maybe say it's 1.5, 3/2, something like that. Definitely positive. So the slope of the red curve at 4 is about 1.5-ish. Again, we're totally winging this. And now all these green lines mean nothing. I don't need them anymore. All I'm doing is connecting these green dots. Now I was winging this, so it's not super accurate, but can you kind of get the shape of the graph here? This graph is kind of coming in like this and going out like that in some fashion. It's a little ugly, but this makes sense. This is x to the 3rd, and you guys remember the power rule from back in the day. The derivative of x to the 3rd is 3x squared. Does that look like an x squared graph? It kind of does. Looks just like a parabola. And here's something even more awesome. As I trace the red curve, my pencil is going, watch this, it's going up, 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 and up. And notice the derivative is positive. Positive, 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 positive. We're moving up, and the derivative is positive. We're moving up, slowing down, slowing down, slowing down, stopping. The derivative is positive, but less positive, less positive, less positive. It tells me I stopped going up. Fits perfectly. And then the graph is going down, 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 and the derivative is negative. Negative, 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 negative. We're going down pretty slow. We're speeding up, speeding up, speeding up, speeding up. We're going down really fast right here. And then we're still going down, but we're slowing down, slowing down, slowing down. We stopped going down. And now we're going back up, back up, back up, back up. And the derivative is telling me that. right at this x value, we've started to go back up, faster, 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 faster. This is how you sketch derivatives. Let's do another one. So this time I want you guys to try it without my help, and then I'll go over it. So I'm going to have you guys pause the video, try this on your own, and then come back and check. Alright, so 3, 2, 1, pause. Welcome back. We're sketching both f prime and f double prime. This isn't much of a job, right? Because once we have one, we're just repeating the process and sketching the derivative of that one. So we have a linear segment. I can count the slope of a linear segment. Looks like we're going up 1 over 1, up 1 over 1. Remember, it's left to right. So this has a positive slope of 1, and this behavior continues forever. So positive slope of 1, you can't take a derivative at a jump. And then what's the derivative of this? Pick a point, sketch a tangent line. So if I was at 1, tangent line right there looks like maybe it's 1. If I was at 2, that's not as steep. That's at like a half. So 1.5. 3, I'm like down here at a third. 4, I'm really flattening out to like a fourth. I see what this is doing. This is creeping in towards, this is flattening out. It's almost flat up there. So this is creeping in towards 0. Maybe over here we're a little bit steeper. So I'm going to start here, and this derivative looks like that. The derivative of this never goes negative. We're always going up. We're just slowing down, slowing down, slowing down until basically we're at 0. And now we just play the same game again. If this was my first derivative, this is my second derivative. Clearly the slope of this linear segment is 0, so the second derivative would always have a slope of 0. Can't take a derivative at a jump. And now what is the slope of this curve? Well, right here, if I drew a tangent line right there, it would be pretty negative. It's decreasing now. So I'm going to be somewhere down here, -2, -1. And then these tangent lines slowly flatten out to 0. So the second derivative actually looks like this. Isn't this fun? Let's keep going. Yes. On to the next. So here are a couple. You guys only have to sketch the first derivative. Here's f of x. Here's f of x. I want you guys to take 2, 3, 5, 10, however many minutes it takes. Sketch the derivative. Sketch the derivative. Pause the video, and then when you unpause it, a little math magic, I'll have the derivatives up on the board. Maybe I'll just draw them. I'll draw them. Pause the video, and then I'll draw them with you guys. All right, 3, 2, 1, pause. All right, a little bit quicker now. Linear segment, increasing. Looks like maybe I'm going up 2 over 1-ish. Again, we're estimating this. You might be slightly different than somebody else, but if you're positive, you're positive. So you can't take a derivative at a cusp. The derivative is 2. So I'm going to take a derivative at 2. If you're already thinking the way I hope you are, this kind of has the shape of an x squared. And the power rule says the derivative of that is 2x. So the derivative of this should be a line, right? Right around 4.5 is when the tangent line has a slope of 0. Everything after that is getting steeper, 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 more positive. Everything before that is super negative, and then it's less and less and less negative. So I'm thinking, just going to draw a line somewhere like so, and go right through that point. There is my derivative. Ain't she pretty? This one's a lot less pleasant, isn't it? But we got this 0 point right here. So right there, I will plot 0. And what are happening to my tangent lines? Well, if I drew a tangent line right here, it would be very negative, and then it would be less negative, less negative, less negative. It would very suddenly hit 0. And then it's getting steep very fast until it's infinitely steep. So it's going to almost look like a line. This isn't quite a parabola, but it's pretty close. So I'm going to draw kind of a line-ish shape, and then I eventually am going to approach this asymptote. This is getting infinitely steep, so the derivative should show infinite slope eventually on the left side of the, or on the left side of the asymptote, rather. What's happening here? Well, I have to be careful. It's really hard to tell what the tangent line looks like at that point right there. So I'm going to work my way down the curve and pick a point at -1. The steepness there, well, I can see that it's negative. If I pick that point right there, and I drew that tangent line, that has a steepness of about -1/2. So I know I'm below the x-axis. Get rid of that point. So the slope at -1 is somewhere down here. And then I can see that I'm flattening out to 0. No derivative at a jump. So it looks like this. And then as I take my tangent lines and creep up this curve, they're getting more and more and more negative until they're infinitely negative. So this actually flips and looks like that. Strange. Let's keep playing the game. Tangent line there is 0. Then what happens, this is a positive slope. Positive, 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 very positive. So I'm going to start my derivative pretty positive. It creeps its way down to 0. And then it's negative, 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 really negative in here. So this is kind of coming down like so. It gets really negative in here. And then it gets less and less and less negative until it's almost 0. So it's going to change behavior and then flatten out. Really tough to sketch that bad boy right there. The slope on, once you pass this point, you're always going down. You're moving down, 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 down. Don't think of it as value. You are not plotting value. It doesn't matter that this is below the x-axis. It doesn't matter that this is 8, -3. That's an irrelevant point. What matters is your pencil is moving down, steeper, 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 very steep. So the slope value at that point is very negative, -2, -3. And then it slows down. Your pencil's still moving down the curve, but it's not moving down as fast. So your negative values aren't as negative anymore. You've got to try to train your brain to think in terms of slope and steepness. Let's do a few more. Okay. So off we go. Again, I want you guys to try both of these on your own. So sketch the first derivative, sketch the second derivative, pause the video, try it, and then come back and you guys can watch my tutorial. Here's my pretty little mug right there. You guys are going to miss me tomorrow. All right. 3, 2, 1, pause. All right, we're back. What does our derivative look like? Hopefully you guys knocked out the middle. Doesn't take super long. This is down 1 over 1. So that is just a horizontal segment. Can't take a derivative at a jump. And of course, if the slope of this is -1, the slope of this is 0. So there is my second derivative in the middle. You're always going to have open circles at these jumps and these cusps and these corners. You just can't take a derivative there. What about this curve? Well, if I picked a point at -7, you can clearly see I'm about negative, maybe -1. So we'll wing it, and then I'm flattening out to 0. So let's sneak an open circle in there. This is flattening out, and then it creeps away, like so. This is going to be super negative over here, so the value is going to be super negative. What's the derivative of the green curve? Well, the green curve, if I picked a point right here, now the slope is positive, and it's flattening out to 0. So the second derivative actually looks like the original. Something like that. And there is my original. upside down parabola looks like this, right? The derivative would just be this. So as I sketch, I want to graph something that looks like that. Here is my maximum. Slope of a tangent line would be 0. Slope on this side of the curve is positive. Slope on this side of the curve is negative. So I'd have something like this, and I'm going to be decreasing my way through the graph. Why is the line going down? Because it's negative 2x. And if we decided that it was negative 2x, that makes the second derivative really simple. It's going to be a constant, and it needs to be negative. 1, 2, 3, it doesn't matter what you decide. I'm going to call it negative 2. There's my second derivative. Now we're having fun. All right, hold that thought. Welcome back. Let's do it again, huh? So, one more time. Only now I've really messed with you. Really messed with you. So we're going to do this in 2 parts. This is already the derivative of something. So this is already a collection of slopes. So we got to wrap our brain around that. This is already the derivative of something, but we don't need to change anything we've done so far when we sketch the second derivative, because the second derivative is just the derivative of the first derivative. So I'm going to do this in blue, sketch the second derivative, and then we're going to come back and talk about how to do this nasty little guy right here, okay? But I do want you guys to pause the video, same routine we've been following, plotting tangent line slopes, collect those dots, connect the dots, sketch your derivative. So sketch the derivative of f prime, which is double prime, pause, and then I'll go through it.
All right, you're all good. You can close out anything I had opened, you can just close it.
Okay,
All
cool.
good.
Thanks, Trevor, I appreciate it.
You're welcome.
So
Want
is
me to
it?
shut this one?
Yeah, please. So second derivative over here is going to be really simple. We're just going, what is the slope here? Down 3 over 2, down 3 over 2. Looks like it's negative 3/2. So at that dot, the slope is about negative 1.5. No problem. And then here, well, what are the slopes? So if I'm down here, really close to 0. And then I'm slowly increasing, maybe at negative 4, I'm at about 1. And then maybe at negative 3, I'm getting really steep now, up here somewhere. And this is just getting steeper and steeper. So it's almost the same exact curve. Looks something like this, and we're just going to approach the graph. So there's my second derivative. How am I going to work backwards to sketch the original? Well, believe it or not, the derivative is all the information I need, because I know exactly how the original is moving. The one thing I won't know is where to start. That piece of information is in flux. If all you know is this is how fast something is changing, you have no point of reference as to where that behavior began. So you have to sort of decide this for yourself, and this comes up when we start to integrate. It's called an initial condition. We don't have an initial condition, so we have no basis for where we're supposed to start our sketch. But we know exactly what this looks like. We just don't know where it is. So you get to pick this. You have to choose where are you going to start. And I'm going to make that choice deductively based on the behavior of the red graph. The red graph is the slope of what I'm about to sketch. This is how fast I'm moving. How am I moving? Well, according to the red graph, at negative 6, my slope is about negative 2. So that means I'm moving down. So right here, at this point, I know I'm moving down at a rate of negative 2 over 1. Keep playing this game. At negative 4, let's say, right here, this coordinate on the red graph is negative 4, negative 1. Negative 1 is the slope. This is the derivative, so that is the slope. So my original curve is moving down at a rate of about negative 1. Then what happens? Something really unique happens right here. I stop moving down. The original graph had a negative slope, negative slope, negative slope, negative slope, 0 slope. And then what starts to happen after? Now the value, the coordinate at these places is now becoming positive, which tells me the derivative is positive and my pencil is moving up. So if I start by moving down, 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 I hit this point, and now my pencil is supposed to be moving up, 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 up. What is this going to look like? Well, since I start by moving down, I'm going to start moderately high on the graph. You can pick this point anywhere you want. I'm just going to start right there. And at that point, the derivative's value is negative 2. So that means I'm going down about negative 2 over 1. So from here, I'm going down about negative 2 over 1. Down, down, down I come. I keep moving down, but I'm slowing down, slowing down, slowing down, stopping. So I come down, 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 I'm slowing down, slowing down, slowing down, I stop right there. It says stop moving down. So I stop moving down right there. Again, this curve could be anywhere along the graph. And now I'm moving up faster, 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 very fast. So this curves up very quickly, and it's going to look like a sort of a non-symmetrical parabola. If you don't trust your graph, then sketch the derivative of the green curve and see if it looks like the red one. A little bit easier to sketch the function that came before a line, because we kind of already talked about this. What came before a line? Well, before a line comes a parabola. So I feel like this should look like a parabola when I'm all done. Right here, the values are very positive. At negative 1, the slope is 5. This is the coordinate negative 1, comma 5. This is my slope of the original f of x. That means my pencil's moving up very fast. Since my pencil's moving up very fast from this point, I'm going to start really low on the graph. I'll start right there. Why there? Just 'cause. You can pick wherever you want. Wherever you want. We have no idea where to start the original f of x graph. But since I'm moving up very fast, I started very low. It's getting me choked up, it's emotional. And now what happens? So I'm still moving up, just not as fast. Maybe here at 1, this point right here is the coordinate 1, comma 2. And this is supposed to be my slope. When you are working backwards, you are looking at slopes. So my pencil's still moving up at this point, just not as fast. And then what massively important characteristic is happening a little bit after 2? The slope is no longer positive. We stop moving up. So my pencil is moving up very fast, not as fast, not as fast, not as fast. And then right when I get to here, I'm no longer moving up anymore. What happens after that point? The slope here is negative 1. The slope down here is negative 2, negative 3, negative 4. So that tells me that I'm going down faster, 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 fastest. It's very difficult to train your brain to think in reverse. So let's do one more. All right, last graph that I want you guys to sketch for today. This is the derivative. Sketch the original. These are values. This is the slope. I want you guys to try to go back and sketch the original graph. All right, pause the video, try it on your own, make a mess of it, and then you guys can come back and walk through it with me. All right, 3, 2, 1, pause. All right, let's talk through it. So how are we doing? Slope up here is very positive. Now we are talking about value. This is like negative 6, comma 6. So that means my pencil's moving up really, really fast. So I'm going to start really, really low down here and kind of have an arrow that's coming up. Doesn't matter where you start, we have no idea where to start, but I know I'm going up. I'm going up very fast, and not as fast, not as fast, still going up, still going up slower. I stop going up at -3. So this is going up, 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 up. I stop going up at -3. Now this is a jump, but since we're working backwards, maybe we're defined here, maybe we're not. In fact, if the derivative exists at -3, the graph has to exist at -3 also. Notice my pencil's moving up the entire time. The entire time my pencil is moving up. And then it stops moving up, but we don't have any behavior. After that, we gotta jump down here. This is a derivative. This is a derivative. This is the slope. What is the value? The value here, let's just say at -2, is about -3.1, -3.2, below this asymptote. The value, the coordinate, right there, is -2, -3.2. And that is a slope. That means my pencil is moving down, pretty quickly moving down. So when I draw this, I'm drawing the slope with that value. Oh my goodness, how many things we got? There we go. So at this dot, I'm already down here below -3, so I'm going to start really, really high on the graph. Again, I have no idea where to start. So I'm going to start really, really high. And I'm at -3, and then suddenly this coordinate is 0, -4, which is moving down even faster. And then this coordinate is 1, -5.5, which means I'm moving down even faster. So from this point, I'm moving down fast, and I'm only getting faster. So this is massively steep. Looks something like that. Oh, you stinker. Ooh, it fixed itself. It heard my threats, and it's like, come at me. All right. What about this little section of curve right here? This is really weird, but we're going backwards. This is the derivative of something. So these are steepness, this is slope. And this point right here, at like, I don't know, 2.1, is super, super steep. It's like 2.1, 3. I guess maybe it's not that steep. So we're moving up pretty fast. At this point, we're moving up pretty fast. And then we're moving up still fast, and then almost instantaneously, right there, at about 2.3, the derivative's value, positive, 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 it's not positive. Pencil's moving up, 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 it's not moving up anymore. So drastic change here. We're moving up, and then very quickly, we stop moving up. I'm right on top of the asymptote. Don't be on top of the asymptote, slightly to the right of the asymptote. And now what does it say? Now we're moving down, faster, faster, faster. Now we're flattening out at a downward rate of really close to -3. So that tells me this is curving, curving, and then we're basically just going down 3/1 the rest of the way. That is what it's called the antiderivative. It's what the original f of x would look like based on the blue f prime graph. It's pretty fantastic, I know. It's pretty awesome. Your calculator can do all of this too, but I'm sure you guys are super eager to listen to me more on this video, so I'm going to stop. You guys don't have any homework tonight, as long as all this made sense. You'll do a little bit more sketching tomorrow in the abbreviated classes for homecoming, and then I'll see you on Monday. You guys will have a lab on Monday. It'll just be more of this. This is one of the most important skills in the entire class, is that you guys can sketch both forward and reverse. Automatically go up a point on the AP test if you guys can do this without issue. All right, that's it. I'll see you guys on Monday. I won't see you tomorrow. Thanks for tuning in.